So we have now problem number 5, which is 2461. It's a coaxial cable. This is the outer part of the cable, which has radius B. And this is the inner part of the cable, which has radius A. And this is metal, is a conductor. And the outer sleeve is also a conductor, and this is vacuum. So inside here is a cylinder inside a cylinder. We have on the inner cylinder, which must be on the outer surface of it, we have a charge plus lambda Coulomb per meter, and we have on the outer shell of the cylinder, which will be undoubtedly on the inside, minus lambda Coulomb per meter. So the net charge on the whole thing will be 0, because we have here the same amount plus per meter as we have here minus per meter, and you're being asked what is the potential anywhere in space, here, here, and there. The trick always is as follows. First, you calculate what the electric field is at any location r. And then the second thing you do is, you say V at position 1 minus V at position 2. It's the integral in going from 1 to 2 of E dot dr. And if you prefer the definition in going from 2 to 1 with a minus sign of E dot dr, that will give you, of course, the same answer, whatever you prefer. Very well. Let's now first look at R is smaller than A. It's very clear that E equals 0 there. But let's go for R larger than B, that is outside the cylinder. It's clear that if you apply Gauss's law, that you will also find that E equals 0. And I will leave you with that. You will make a Gaussian cylinder with a radius larger than B, and you give it any random length you want it to give, I don't care, and you apply Gauss's law, and you will find, since there is no charge inside that cylinder, that the electric field will be 0. So outside 0, and here in the core 0. What now is the electric field between A and B? That's really the only part where you have to do some calculations. Well, I now inside this vacuum produce a Gaussian cylinder, coaxial. It has radius r, and the radius is larger than A and smaller than B. It is clear that the electric field everywhere on the bent surface will be pointing radially outward. There's a positive charge here. I don't even have to worry about whether it's inward or outward. It will surely be outward. So let's draw it just here outwards. And if you can see this here, the idea is that it is outward, perpendicular to the surface. And the ds values themselves are of course also perpendicular to the curved surface. So E and ds are in the same direction. So if you were to look from above, this is the radius B, and this is the radius A, then the electric field will be in this direction, even though it will be stronger here, as you will see, than it will be there. Now I apply Gauss's law. The E field everywhere on the cylinder must be the same for reasons of symmetry. I take the length of the cylinder arbitrarily L. And so the flux through that cylinder equals 2 pi r times L, that's the surface of the cylinder, times E. The dot product becomes a +1 because ds and E are in the same direction. And that now must be the total charge inside, which is lambda times L divided by epsilon 0, because L was the length of this cylinder. And the L cancels, the L better cancels, because it would be absurd if the E field depended upon the length of my Gaussian box, and I find that E equals lambda divided by epsilon 0 2 pi r. A very famous result. It's inversely proportional to 1 over r. With a sphere, we had an electric field falling off as 1 over r squared. With a cylinder, we have an electric field falling off as 1 over r. Now you can imagine what you might have if you have two very long, infinitely big plates. Maybe the electric field doesn't fall off at all. Because think about it, a sphere, electric field falls off as 1 over r squared. A cylinder, it falls off as 1 over r. So maybe two parallel plates, the electric field doesn't fall off at all. Maybe it's constant inside. We'll get to that. All right, let's now talk about potentials. The potential at point B, at the surface, I call that point B, is outer surface, is 0, because the potential at infinity is also 0, and so there's no E field all the way from the outer shell to infinity. So if this potential is 0, then that potential is also 0. Now if this is the outer radius B, and this is the inner radius A, what now is the potential here at this radius r, where r is smaller than B and larger than A? Well, if I go from here to there, and I use my shorthand notation, VR minus VB, B is any point then on this cylinder, that equals the integral in going from R to B of E dot dr. The dot becomes a plus 1 because the cosine between the angle between E and the R is plus 1, so I don't have to worry about that. And so that becomes the integral in going from R to B of lambda divided by 2 pi epsilon 0 dr over r. So we just calculated. Now this integral is the logarithm of r taken between the value b and r. So this becomes lambda over 2 pi epsilon 0 times the logarithm of b minus the logarithm of r, which is the logarithm of b over r. So that's the way that the potential changes from here to here. And if you want to know what it is at r equals b, well, you put in r equals b, and what do you find? No surprise, the logarithm of 1 is 0. It's exactly what we had. If you want to know what the potential is at r equals a, then you put in r equals a, and you find here b over a. And so I would like to make a drawing now of the potential as a function of r. Here is b. Here is a. I know that right at the center, well, let's start at infinity. So right at infinity, all the way, potential is 0. And then it will climb up to a certain value in this logarithmic fashion that we just calculated. And then, since the inner core is metallic, there is no E field in that inner core, and if there is no E field, it's an equipotential, and so it will stay there. And the value here, everywhere inside that inner core, the potential is lambda 2 pi divided by epsilon 0 times the logarithm of b over a, and all of this then is correct because v at infinity equals 0. That's why we talk about the potential rather than potential difference.